Stop transcription.
I mean, it looks like the transcript is pretty accurate. It got you there.
All right. Welcome back, everybody. It's a new year. Another year at SEAAK. I'm still the president. If anybody wants to step up and become a vice president next year, we're always looking for members and officers. We're going to go over this treasury report real quick, Magda. Pull the full page here. Oh, you can't see that.
All right, so we started our new year 2025 with $14,361.33 in the account. And for the already within the 2 weeks, we got 36 new memberships that came to our account and 2 corporate memberships. So currently we have in our bank account $16,977.63. And of course, new year, we're going to have new expenses paying for different type of membership with the National Council and get our webinars and things like that. So anyway, thank you very much for everyone who already paid the membership, and we encourage you, the rest of you, to also make the payments. Thank you.
I'll pay soon.
So you, because I paid
Yeah,
went through that, so now, okay.
So you're already on for the next year?
Yeah,
This year?
New year, new payment.
I'll send the check.
Okay, well, we get a corporate membership, which includes 2, and then we'll have another membership, and we obviously pay for those. So SEAAK and CSEA updates, we're working on the roster. We're gonna do continued webinars. If anybody's interested in being a corporate sponsor that's not already, look into it. E-Week's coming up. I personally am not doing a lot for E-Week. I don't know if anybody else is, but I'm sure you'll see stuff coming out from employers, whatnot. It's a good thing. I mean to do it. I'm just too busy coaching kids to play hockey and raising teenagers and running this, and then working to continue doing it.
I'll plug Hamill's Balsa Wood Bridge competition as part of E-Week that he's trying to do. I think every year he needs around a dozen volunteers. These are PIPs, for middle school and early high school.
Okay.
Building and load testing and everything. So last year went pretty good, but he admitted he was a little late in getting out requests for help. So I'm sure you're going to see, people on that email chain are going to see some additional requests when not enough people sign up.
Okay.
I think we'll get yelled at.
Okay, we'll jump on that a little bit there. So leadership outreach, I already touched on this. I'm still sitting in as president, still have the same treasurer. Our secretary is getting a little bit more busy at work. He's still managing it, but we'll help him, and anybody else that wants to jump in and contribute or work with us, you're more than welcome to help out. Next board meeting, we're gonna do February 19th. It's a third Wednesday of February. Either myself or Jake will be sending that out, and it's a renewal year for your license, so don't forget your PDHs. Those are usually on Thursday mornings. I haven't been able to attend them, but I'm gonna start attending them. I'm tired of the project meeting. I get stuck in on Wednesdays, and I can probably do everything in the first half hour of the meeting and then skip out on it. So with that, I would like to present Alex Dado. Did I get it right?
Enough. Yep.
Right.
Dado.
So Alex came up a couple years ago at UAA, and we did a load testing. It was really cool. We spoke pretty recently, and he's got some updates to FRP. And I know also a couple of us don't really know about FRP. It's really useful if you need to do seismic retrofits, punch holes in reinforced concrete. You got degrading rebar, degrading strength, you need to fix it up, so. Gonna hand it off to him, and then also he sponsored lunch. So everybody, don't forget at the presentation, this I think was also, we'll send out this QR code in an email. But if anybody wants to hit that QR code right now, we're signing in. This is how you'll actually get signed on for your PDHs through Simpson Strong Tie this time around. Okay, so with that, I'm gonna see if I can't maximize this screen. In here. Oh, hold on. I'll just turn all this off maybe. That might be as good as I can get. Yeah, okay.
What if you hit pop? What if you hit pop out?
Is that good enough? What did it pop out?
Maybe. And maximize.
Perfect. All right, Alex, floor is yours.
Great. Well, yeah, I appreciate everybody having me and coming to watch today. The QR code, it'll be up in the upper right for every slide, so no big rush. Yeah, if you need those PDHs or CEUs, that's the best way to get them through Simpson. A little bit about myself before we dig in. I was a consulting engineer kind of up and down the coast of California before I joined Simpson in 2019. And part of my original territory was Alaska. So early 2019 when I got my engineering license in Alaska, and I was servicing you guys all the way through mid-May 2023, I want to say. Took a little hiatus in SoCal, and now I'm back. So I'll be based out of Sacramento, and I'll be coming up usually in the winter. So I've found that it seems like everybody's busy in the summer, so it's better to come bother you over the winter. And a little bit of this presentation was covered in the last workshop that we did, but we've done subsequent testing on the same programs, so it's an update on those. And then the last slide kind of talks about some of the newer testing that we're ongoing with and what is coming down the line for testing that we haven't started yet. And that's what I would be hoping to come talk to you about later this winter, if anybody has any interest past today. So that trip isn't scheduled, but please reach out if you do want me to come by. That'll help me target when to be there. And today's presentation is going to be called Advances in Fiber Reinforced Polymer. I would not say this will be the easiest presentation to wrap your head around if you're completely unfamiliar with FRP, but I did build into the presentation some of the basics. So anybody that has never seen it or heard about it will get some of that basic information, start to understand what it's used for. This is the general agenda. I should be done right at, I guess it'd be 1 p.m. your time, 2 p.m. my time. But please ask questions. If we don't get through the content, it's much better for me to get you the information you actually want. So yeah, I'm happy to stop. I won't be able to monitor the screen that well, so just speak up if you want me to stop, and or if I need to slow down. I've been told I talk a little fast sometimes.
You do have about a 2 to 3 second delay, but it's nothing undoable.
Okay, no, that's good to know. I'll try and hit the button a little bit early. But yeah, today we're going to do a little bit of basics, importance of code reports, where we are with FRP, getting into the code, and then really dive into testing and applications after that. So I like to start very, very basic. What is FRP? Because it's an acronym and some people don't even know the acronym. So FR is your fiber reinforcement, and for buildings that's either e-glass or carbon, that provides the strength and stiffness to the system. And then P is your polymer resin, which is almost always epoxy for buildings, and that kind of makes the fibers composite with whatever substrate you're applying it to. Provides that shear transfer and load transfer and makes this externally bonded reinforcement system function correctly. So I'm only going to talk about FRP today. I do work with another system, FRCM, which is a carbon fiber grid and cementitious matrix. It has very similar applications to FRP, but it goes on to rough surfaces a lot easier than FRP. So yeah, if you have any projects that, basically what I generally tell people is it's concrete, block or brick and it needs additional strength or repair, you can call me and I'll help you through the whole process. We do a little bit of work on like large members of wood, so glulam beams and mass timber, that kind of stuff. FRP can help. It's just less common, so I don't talk about it too much. But that's the basics on FRP, at least on a very granular level. And now we'll start to look at applications a little bit. So this is typical placement of FRP reinforcing on a gravity system for gravity strengthening. So where you would see steel is very similar to the layout. You're going to see FRP, but instead of a round steel bar, we're going to have sheets of fabric applied to the outside. So if you have a flexural issue or flexural cracks developing, we can put a longitudinal strip for, this would be positive moment reinforcement, and kind of provide more tensile capacity, get that system to work. Very similar if you have shear, we're going to apply the FRP in what we would call a U-wrap, essentially going down one side of the beam around the bottom and then back up. So very similar to a stirrup. If that stirrup needed 135-degree bar bends, we would actually use an FRP anchor, drill that into the substrate, and that'll anchor it off and be very similar performance. And then if we needed to make a close tie and your slab was actually in the way, we would use an FRP through anchor again to drill up through the slab and close that loop. That way we can get closed ties. So that's for the beam. We can do similar things for slabs. Slabs, we generally only address flexural loads. Fear for slabs is not well studied yet, so I don't recommend it with FRP at this time. And then for columns, at least for the gravity case, one of the most common applications of FRP entirely is a confining wrap, which is what we're seeing here, where we wrap horizontally all the way around, just like your closed ties. And we're picking up that actual cover area, so you get a little bit of benefit from just having more effective concrete, and then the FRP itself is confining the concrete to bring its compressive strength up. How does FRP get through things? I kind of buried the lead a little bit, but we use FRP anchors to basically close that tie, and it is tension only reinforcement. So when we have a through anchor like this guy here, we're basically grabbing this strip of fabric in its parallel direction and transferring that tension through the element. So we're not depending on a through type anchor, just tying things together. Some more common applications, and these kind of work more into the lateral world. Went ahead, but new slab openings, that happens on new construction. For new construction, we put it in the construction remediation category, where somebody made a coordinated, and now we need to open up a hole where we didn't plan it, and FRP can just approximate the rebar that was cut in that hole, and we can redistribute the loads around the opening. For the lateral case, you can do this kind of trim bar configuration to help with force transfer around the opening. We covered column confinement, but column shear looks just the same. It's going to be horizontal wraps, and there are aspect ratio requirements, all that I can help you with to check to see if your column will work. But yeah, for columns, we can do shear reinforcement, confinement reinforcement, and flexural reinforcement. And then walls, we're going to talk about quite a bit today. This graphic is actually showing what I would call an out of plane reinforcement, where we have distributed vertical strips along the length. Inside the case, and that will pull back and forth. It is only tension reinforcement, so you're going to have to put it on both faces. If you have an unreinforced wall, we can actually saw cut into that wall towards the center line and add a pre-hardened bar of FRP and get away with a single-sided application. But that actually comes up quite a bit. I would say the majority of my FRP projects up in Alaska have been column confinement and wall out of plane reinforcement. For in-plane reinforcement, you'll see distributed horizontal strips, just like you would with steel bars. And then if you have in-plane flexural reinforcement needs, we're going to have discrete strips on the ends of walls, kind of like boundary elements, taking that TC out. So these are common ACI 440. ACI 440.2 is the design guide that covers FRP design. And you could pull that reference document, look through it, pull a manufacturer's data sheet, and you'd be able to get to a solution on your own that way. The caveat that I give is it's not codified. And as we have been testing through things more and more, and you'll see some of that today, we're recognizing that document is built on more university scale testing, smaller members, smaller layups of FRP. And when we get into practice, we have full size members and much thicker layups of FRP. So the equations don't always give you, well, it's hard to achieve what the equations promise without proper detailing, basically. So that's my first big call to action, is give me a call if you're working on it. Even if you understand ACI 440, I'm sure we can help and help ensure that you get the performance you're looking for. The second on this slide is this little detail over on the right. So this is a slab to wall shear transfer. It can do, say, roof to wall, floor to wall, or wall down to footing. And it's an in-plane shear transfer. And because the fabric goes around this inside corner, so from a flat surface to a vertical surface, that is not covered in ACI 440. There'd be no equations for it. And we just build full-scale specimens. We've run them with lightweight concrete, masonry walls, concrete walls, normal weight concrete, just a million different configurations to get capacities. And that's not something you'll find in our literature or really online or in the ACI document. You just have to give us a call and talk to us about your project, and then I'll propose it as a possible solution. But we have lots of applications like that that are not covered in ACI 440. All right, now we're going to talk code reports. IATMO and ICC both have different acceptance criteria, basically, for FRP. Depending on your jurisdiction and really just generally as an engineer, it's good to have a code report for the system that you're using. And what we like to point out is it's important to note when you're looking through these code reports, go into the approved applications, because there's lots of durability testing, and basically these reports are founded on quality testing and then reviewed by the code agencies. So if that application isn't listed, there's probably a good reason that it's not in that report, and you probably shouldn't use that material for it. So that's IATMO. ICC looks very similar, but if you go into our reports, you'll see we have pretty much a full seismic rehab approved at this point, from diaphragms to diaphragm to wall connections, wall reinforcement, and a lot of things in between, basically. Good to have a code report to support the system that you're going to be using. This slide is just a quick update on where FRP is with the code. So ACI decided to add PRC in front of anything that's a design guide and not officially a code yet. So ACI PRC 440.7 is actually the masonry code, and PRC 440.2 is the concrete. But they're targeting having it actually in the code by 2025, which means adoption will be years later, but that'll be the first time ACI lists an actual FRP code. They're also trying to work seismic retrofit guidelines for FRP into ACI 369, and that is targeted for 2028. And then probably the one that'll come out the soonest is more of a California thing. DSA is the Department of State Architect. Oshkosh HCI is the hospital jurisdiction down in California. And we have design guides, and our competitors have design guides into both of those agencies for review. And as soon as they give approval, that'll be kind of the first code agency that has listed how you design FRP. So that's just a quick update on where we're at. And now we'll look more into the testing. So yeah, a lot of slides to get through. Please ask questions. I am happy to stop and slow down. But I always start with acknowledgements, because I know it's hard. I used to be an engineer, so I know it's hard to just trust what a manufacturer's saying. So this slide is really just here to show you that we are working with people out in the industry, and people are checking our testing and really kind of confirming our thoughts or denying, and then we have to come to a middle ground. So most of our testing has been triggered by Oshkosh HCI for hospitals in California. We hired Dagan Kolb to give us more information on available inventory of buildings. So we can target our tests to cover as many buildings as possible. We also use structural focuses services for that. And then we hire Degenkolb for back-end analysis when we need backbone curves and modeling parameters for ASC 41. Okay, so now we're going to talk diaphragm shear strengthening. Big note that kind of triggered this testing is ACI 440 doesn't actually cover diaphragm strengthening at all. ACI 440 has provisions for calculating axial tension capacity of FRP ties, which is kind of the first foray into diaphragm design. You can take that tension tie, compare it to in-plane reinforcement cords and collectors. So 440 has that. So does the CNR, which is the Canadian code, and then the FIB bulletin is the European code. We're going to see a slide in I think 2 slides from now that kind of compares results from each of them. But when we got into the databases of FRP tests available, kind of realized what I alluded to earlier. A lot of the testing out there was done with like 11-ounce 1 layer of FRP. So 11 ounces is about the lightest fabric you can find. And then actually the slab or concrete size of those tests is the most startling. Some of them were on 2-inch pieces, 2-inch thick pieces of concrete. Some got up to 4, and then even less got up to 6 or 8. Yeah, we just looked at that and we realized, yeah, there's just not that many buildings built with a 2-inch concrete wall in them. So we wanted to go kind of more in depth. The last one is ICC and IATMO have different design guidelines. When you dig into them, they use different equations for calculating FRP debonding, which is the most common failure. At a certain point, you get so much tension in your FRP and it's stretching, and the concrete can't stretch as far, and then it just kind of peels off and unzips itself. And we'll see some slides of that as well. So those are the reasons we wanted to study diaphragm shear strengthening. Here's the 2 different equations I alluded to. So IATMO's on the left, and ICC is on the right, but essentially this is your debonding strain. Your debonding strain is kind of built into this equation here, but the basis of those equations is different, and they actually set different limits. ICC just pushed the maximum strain achievable or allowed to be used with FRP up to 0.5%. IATMO still has it at 0.4%. And our testing actually shows that it's nearly impossible to reach those values unless you really anchor your FRP off adequately. So there's about a 25% disparity in capacities, and then those capacities are hard to achieve unless you detail it. And none of the design guides currently require that FRP is detailed. Essentially, ICI 440 would, if you wanted to compare it to 318, 440 is at the point where it can tell you need a number 5, but it doesn't tell you that number 5 needs to be bent at the end and tied at 16 inches on center. And that's what all of our testing is getting us to, is how to actually detail this so you get that performance in your seismic event, not just for that first big lunge from the earthquake, but post-peak performance as your building shakes apart. And we want to make sure it all holds together throughout.
Hey, Alex, I'm
Yes.
kind of ignorant with what is IAPMO?
IATMO is it was a code agency that focused specifically on like mechanical systems at first, and then I think in the last decade, I might have to look into that a little bit deeper, but at some point they decided that they're going to start running additional programs and coming into the more structural realm.
Okay.
So ICC has more stringent requirements to get a code report through them, at least in my opinion. But IATMO is another code agency that very similar to ICC, essentially.
Thank you.
No problem. So FRP ties versus predicted values. So this is the slide I was talking about, comparing the FIB bulletin to ACI and with real test results. So the slide is actually courtesy of the University of Auckland. Professor Enrique came to our lab to run all this testing. Our lab is in Stockton, California. So we have 16 active test programs outside of the Simpson Strong Tie labs right now with various universities And yeah, there's a lot of development in FRP right now. Pretty much anytime you see me, I will have something new to tell you about. But the green line here is if you could activate full strain of the fabric to rupture. The blue line is actual test results. Black and gray are what the fib bulletin predicts. So that gray line for fib's actually not bad, a little bit conservative. We like that. But what's scary for us is the ACI equations. Once you get to one layer of a thick fabric, they remain accurate or conservative to a degree. But once you build up thicker than that, they start to be inaccurate and overpromise performance to the tune of about 100% when you get to your thickest layups. Most FRP applications I see for seismic applications are in the 2 to 3 layer realm of a 44-ounce fabric. So we would be out here in this unconservative range. And the testing that I'm going to go through today kind of tells you the story of how we get this blue line to start to match this red line. That way we can actually achieve the maximum performance that ACI 440 promises.
And what's that black calc for IC?
Black calc for IC. So end peeling is one failure mode in the fib, which is basically just debonding that starts from the end of a member. So we usually look at that for flexural members. And then IC, I would have to look up the acronym, but it's essentially fibs just debonding in the field of the fabric. So at your high stress location instead of the end.
Okay.
And that kind of, if you look at it, kind of starts to make sense because end peeling will typically govern for a flexural case, and we take a higher debonding strain for flexure. If you imagine on the bottom of beam you have FRP, it goes into tension, so it wants to stay as straight as possible, but that beam is deflecting down, and that downward force against the tension that wants to stay up gives you a higher bond capacity.
Got it. And so, yeah, obviously in that, or well, never mind, that's not a test, that's a calc value. Okay.
Yeah, that's a great question or great thing to bring up. Essentially, we still use the ACI 440 equations, but then we detail out the FRP so we know we're going to perform the way they promise. And that's the way it's currently designed. But FRP capacity, when it comes down to it, it's pretty simple. You calculate your debonding strain, and then you times it by your area of fabric and your modulus, and that's your tensile capacity.
You were talking end detailing. Can you actually get it to behave more in that IC case? Like if you preclude, is there a practical way to preclude end peeling?
Yes, yeah. So generally, and we'll get to the end of the recommendations, but what we do is we put anchors sized to rupture the fabric out at the ends. So a large anchor at the ends that prevents end peeling. And then we put smaller distributed anchors along the length that basically we have testing that shows even if we lose bond, if we get those anchors right, we can still achieve the strains promised and we can still get the performance promised.
And you would think that tested value would be closer to the black line then.
Yeah, it actually is in reality when we look at the tested capacities, but we still stick with the blue line because that's what's released by ACI right now, and yeah, Simpson doesn't want to overpromise what the code agency or code officials are promising.
Got it. And because, like you said, that end detailing is not codified.
No, yeah, none of it is. ACI 440 recommends anchors, but it doesn't actually give you any idea how to design them. And then there's an acceptance criteria that got pushed through ICC last year that's coming out that delves into that and how they should actually be anchored. But I think we're probably ahead of the game on getting that testing out and everything approved and added to the code report, but it's going to take a while for people to catch up. Not all the manufacturers have that big lab available to them.
Okay. Well, yeah, thanks for answering my questions and giving an idea of, where you can actually look at the black line in your head. If you know that you've detailed the end anchorage, you can kind of have a nice warm fuzzy feeling that maybe you're actually quite a bit higher than the code.
Yeah. And when it comes down to it for a seismic or wind case, your maximum capacity of your FRP is going to be a strain of 0.4% times the modulus of the fabric and the area. And that'll be the maximum tensile capacity of your FRP. But if you were looking at in-plane shear on a concrete wall, will never get you past the maximum reinforcement ratio. So if you're just doing back of the napkin calcs saying, oh, can this wall ever get there with FRP? Push it up to 10 root F prime C. If that works, then FRP will work.
Thank you.
All right, so this is a case study, and this is repeat for anybody that saw me about a year and a half ago. But again, more testing has happened, so we're still going to talk about it. But this is basically what introduced us to the hospital jurisdiction in California and kicked off this deep dive into FRP that we've been doing for the last 4 or 5 years. It's 10-story concrete building. We're not going to talk about the shear controlled columns. We were able to fix that with FRP, but what we're going to focus on is collectors. And it's a project that was bid out entirely, and then they realized, oh man, COVID started. We need to keep more rooms open than we thought. Is there any way to get away from steel collectors? They had steel collectors specified. Nothing really wrong with a steel collector if you got room and time, but this hospital needed to save rooms, and FRP takes a lot less room to get installed. You imagine trying to fly steel plates or beams into an active hospital. You got to take out the window, fly it in through the side, get it all mounted up. With FRP, we can kind of just do it inside with about 2 feet on either side of the work area and just kind of string it in, legitimately just stitching the building together. So that was basically what triggered everything. We designed the FRP alongside Degenkolb. We ended up being an engineer of record for the FRP design for the project, submitted it to HCI, and then their lead, Ali Sumer, that was one of the acknowledgements at the beginning, said, I don't believe that this will work the way you think it, because he was familiar with the FRP testing out there, and he wanted to see testing with these thick layups that we have in order to approve this project. So he got involved with our test program so we could make sure that anything we test will work for hospitals in California. And it's really one of the most stringent code agencies I've dealt with. But here on the left, this is what the collector design looked like when we took it into HCI. So just a strip of fabric, basically adhered down to the slab, and then some complex connections here that we're not going to have time to talk about. And then on the right is the detailing that we ended up producing after going through all the deep dive of testing. So we're going to look at and see how we got to here from here. So start out very, very simple test setup. It's monatomic loading. Since FRP only works in tension for collectors, we didn't need to test it cyclic at that point. We do have a subsequent test program coming out of the University of Auckland again, where we're going to try and test these collectors cyclically to see if that changes anything. But this is essentially the state-of-the-art testing for now. But we have a full-scale 6-inch slab that's anchored down to the test rig, and then a 6-inch strip of FRP applied to the surface. And then we start to play with anchor configurations and layup thicknesses. So what you see here is kind of the old school. We're going to do 1 strip of fabric, no anchors, and pull on it to see how it performs and where it fails. Looks a little different in actuality. This is white paint with black spray paint flecked on it, and that's for this digital image correlation system to track the strain fields. So the next slide, you're going to see basically the load move through the fabric as it peels off. And here we are. I got to get rid of my laser pointer. But this is essentially how unanchored FRP performs and behaves. We're going to be pulling up. Oh, you can't see me anymore. We're going to be pulling up right here. And then we're going to see load start to develop here, and this whole field will change color. As it changes color, there'll be this regular purple color down here. That's FRP that hasn't seen any load, and then anything that's changed color is either debonded or in the active bond zone. And the active bond zone is the portion of FRP that is transferring load to the concrete or from the concrete into the FRP, depending on how you're looking at it. But what you'll see is we'll build load here. At a certain point, we'll hit the debonding strain, and that active bond zone is going to travel down the end of the strip. And when we run out of strip, we lose all capacity on the right. Let's see that go happen. And there we are. Active bond zone is now traveling down. So you can see it travel down and then it ran out of runway and we lost all capacity. So that is just unanchored FRP, still a pretty thin layup, but we get decent displacement. You actually get a decent load in it. And I get that question quite a bit. You know, if we don't detail the FRP and we keep the layering thin enough that the ACI equations are accurate, is it okay to leave it unanchored? And I say, well, yes, in theory, as long as you're confident the seismic load is exactly what it's going to be, because if it goes 10% higher and you only left 5% residual capacity, you're going to lose your entire FRP system in that event. So I almost always recommend anchoring it off, even for gravity cases. You're just depending on the bond too much, and it's good to have that mechanical interaction. All right, so the next one is IAPMO basically said, hey, if you do an anchor that's 1.5 times the capacity of your fabric, you can take that highest strain and you'll be able to achieve the highest capacity with FRP. So we wanted to see, okay, big anchor, what does that do? So on the right is where the load's coming in. There's a head of an anchor here, and an FRP anchor is essentially, if it's an embedded anchor, it's a bundle of fibers that get drilled and epoxied in just like a normal epoxy dowel, but then it comes out and it's a loose fiber tail. And that tail gets laminated into the actual FRP fabric and it grabs the fabric that way. So right here is what I'm going to refer to as a splay or anchor fan. That is what's actually connecting the FRP to the FRP strip, sorry, the FRP anchor to the FRP strip. And then where it comes together, that's where the embedment happens into the slab. So this one's a little bit brighter, but the load comes in over here. And what happens is the load builds to where the FRP debonds, and then you see that active bond zone travel to the anchor fan. Once the anchor fan's activated, it starts to pick up more load. But this anchor is so big that the only load that makes it past it is going to be on the sides of the anchor. So at a certain point, we get past the rupture strain of the FRP, and again, the system fails. So performance is better with the large anchor, and you can get that higher strain. But what I don't like about it is this is a 5-foot tall block. So if you had a 100-foot long diaphragm collector and your wall that you're tying off your FRP to is, sorry, up here. So say this is our wall and then our collector extends 100 feet and you put this big end anchor here, you're actually going to rupture your fabric right here and you'll lose the other 99 feet of your collector. So we really wanted to see, can we make anchors small enough to where we achieve the strains in the equations, but also allow load sharing across that entire length. Most buildings don't have a 5-foot collector in them. So this is the end anchor again, but we put it towards the end because industry standard, like what we bid against usually when other designers design FRP, is they'll take that 100-foot long collector, they'll put a big anchor at the opposite end away from the lateral force resisting system, and then basically just say we can take the high strain, and you'll see everything debonds all the way out to that anchor. So instead of this nice even force distribution where your collector's picking up load along its entire length, you end up with a very concentrated force out at the end, about 100 feet away from your actual lateral force resisting element. So I don't like that as well, but you do get that higher strain promise. So it is accurate. If you anchor this off, you can get to the higher strain. So there, and I'll start this over, get my laser pointer. Right here is your active bond zone moving down. So everything up here is debonded. Everything down here is still bonded. And when you hit the anchor, you do start picking up more load, but eventually this anchor is sized for fabric rupture. So the fabric's going to rupture, and that's when we lose the capacity. And this is all slowed down quite a bit. So that debonding actually happens in like a split second. And then when these things rupture, they go off like a guitar string and stuff flies everywhere. Sometimes people ask me about this little step. So I'll go back when I talk about it. But that is essentially due to like practical reasons of the installation of that FRP anchor down here. You can imagine you have a bundle of fibers. It's got to come up and take a hard 90. So anything on the outside edge of that curve is going a longer length than anything on the inside. And when these anchors come into load, that usually ends up with a little end peel of the anchor itself, which you can see there's kind of a yellow halo that forms around that anchor right when it pops. So right before the step. Or right when it steps. So when this jumps down, this will all turn yellow. And that's just the end of the anchor peeling up as those fibers all pick up the load. So again, we like that the end anchor could get that higher capacity, but we didn't think it was a good detail specifically for a seismic case because you end up with that huge stress concentration very far away from where you're trying to get it, and the cracks could go wherever they want. So this is the test that we ran with smaller anchors. So the anchor head is here, the fan goes up, load's coming in from the top again, and then there's another one here with the head right here. So this one, again, we get a nice active bond zone and we get debonding, and then we hit the anchor and we start picking up more load, but the anchor is small enough that all the load can make it past it. And then we hit the second anchor, continue to pick up load and capacity, and then eventually we get to the point where we fail the actual anchors. FRP only works in tension, but this looks a lot like a shear failure where it just shears off right at the top, and we'll see that in a second. But what we really like about this is we can still do the big end anchor, but we can put these little distributed anchors along the length that allow load sharing. And as the system debonds, those anchors will bring load back into the FRP or back into the structure, whichever direction we're heading, even if it is debonded. And we've actually ran these tests again with cellophane between the FRP and the concrete and only the anchors in place, and you get the exact same curve. There's a little bit more area under it usually due to the debonding. So we would never install it without doing surface prep and working on that bond. But we know if we lose the bond, we're still going to get the performance that we want. And this is actually that test I was referring to. So this is the bond inhibiting plastic, and this is where our anchors stick out. And that's that kind of shear rupture that I was talking about as well. So unbonded FRP, if properly detailed, we can get to the capacity we need. And then you just need to understand how your anchors work in order to determine their pattern and diameter. So this is kind of the collector design philosophy. We start with a bonded system and we anchor it off. Load comes from the building into the lateral force resisting system. As the load builds, we'll start to develop cracks. Cracks are essentially a place where FRP is debonded. If you imagine that crack opens, FRP is above it. There's nothing below the FRP, at least for the width of the crack. And debonding typically will propagate from a crack because that's where the stress concentrations form. And once you're over the limit, it just unzips. So as the cracks form, the load gets higher. You'll start to see some of the FRP debond, but we have the anchors in place to keep it performing. And you go into that highest load cycle. And as long as you've detailed it out correctly, you can get that load into your lateral force resisting element and get the performance you're looking for. So we started with just the fabric. All that testing set us up with what these anchor patterns need to be. So that distribution of anchors and diameter affects the strain that we can calculate. And then we use the strain to figure out strain against the desired capacity to figure out the area and thickness or width and thickness. So all of that testing gets us to the point where we know where these anchors need to be, how wide this strip is going to be, but it doesn't actually tell us if those anchors have a high enough capacity. So we went back through, again, tested just one anchor in various configurations. We had embedments at 90 degrees, 135 degrees. We've done normal weight concrete, lightweight concrete. We've even done a little bit on steel pan decks. And you install the FRP unbonded, so that's the hatch, and then you pull on it in the same configuration until you get that anchor to fail. We study that to the point where we understand what diameter and embedment give us what capacity, and then that helps us set how many anchors and what diameter and embedment in this heavily loaded section. So the lateral force resisting element will be over here. And then as we get further and further out with lower loads, lower strains, we start to trim that down to pick up economy. So these are typical FRP anchor configurations. The black and white images are really kind of an in-plane flexural reinforcement vertically on a wall going down the end, and how we would get it through a slab. So that's a through anchor. And then once you get down to the footing, we'd use an embedded type anchor to anchor down into the footing. And then this detail on the right is more of that slab configuration I was talking about, where we have horizontal strips on the top of slab, and then we're drilling in embedded anchors along the length of the strip to get the performance we need. And this is just a little bit on how FRP anchors can fail. So this is all the information we studied to figure out the anchor diameter, but essentially they can fail in straight bond failure. So just pull out. You can have combination like a 90-degree pull out, where they're actually just kind of unthreading from that hole, even though you're pulling against them. So it doesn't fail in shear, it still fails in pull out, even though the load's 90 degrees to the anchor. You can have a rupture failure where we exceed the capacity of the fabric itself. Rupture failure in a bent anchor, that's the one I was referring to earlier that looks more like a shear failure. And we can have splay failure where we've exceeded the bond capacity of the anchor splay to the fabric itself. This one's actually really hard to produce. The bond's really good, so we had to be very specific with this layup to get it to even happen. Not usually a failure mode that will govern. Oh, would you look at that? Something happened to my presentation. That was it for collectors. Now we're going to look at diaphragms. That's what this edit master title should say, FRP diaphragms. And I include this image because it's an older project that we did on lightweight concrete in Oregon in the winter. So the tent is there to keep the rain off of it, which is definitely a problem we've faced up in Alaska. And then this little tube here is actually pumping heat into that tent because it's too cold for the epoxy cure. And we did that on the YMCA building in Anchorage. They actually built a big visqueen tent with positive pressure to pump heat in there and get an installation, I think it was mid-January, up in Anchorage, which is very difficult. Under 40 degrees, epoxy does not cure at all. So you got to get everything up to temp and get it all installed. But that's the main reason I keep this in. Also, this is a installation that occurred prior to all the testing I just showed you. So there's no anchors in this design. And if I ever get a call about this building again, we will make sure that those anchors get added for sure. All right, so diaphragm testing. Got 14 minutes left. I think we'll make it through diaphragms and we'll have to save walls. But this is our first kind of diaphragm test that we did as a study to start building more university-based testing that'll be more in depth. So this is a Simpson only internal test. On the left is the control, but we wanted a shear controlled slab. So we're actually going to load it midway here. These two bond beams are going to be fixed, and then we'll push it to where you get that 45-degree crack from the load point. And that's why you see very low shear reinforcement and higher flexural reinforcement. We want to get that shear failure. So we tested that without FRP, built a similar specimen and put FRP on it. And we did that industry standard where we're just adhering the strip and then putting the large anchor on each end. Now to compare that to my collector, I guess metaphor or simile, whatever it is, this looks great on a 5-foot specimen. Again, if that diaphragm is 100 feet wide and you only have the end anchors, I am a little bit more concerned because you'll often get cracks near the edge of your slab. And if you lose that anchor, you lose the whole system. So even on diaphragms, even though we've tested it this way, I'll show you how we get to a more distributed layout for our recommended detailing. But here's the load setup, again, fixed. And then we have these two big rams kind of pulling on it with steel plates to distribute the load. And you'll see when we get to the FRP specimen, it's too strong to the point where we get a crushing failure and this whole thing kind of explodes and we never fail the FRP. But the control specimen, here's your hysteresis, fails just like you would expect, right? Shear controlled, you get that nice 45-degree diagonal between your last point of support and your point of loading. Not a lot of area under the curve, but we know it's predictable. Predictable enough, at least where we don't get that crushing failure. And then we go to the actual strengthened specimen with FRP. And again, it's painted white, so it's going to be hard to see, but there's strips along it. And we made it too strong, and we get this big crushing failure. So here's the digital image correlation video. Structural tests can be a little bit like watching paint, so this is the slower one. But you can see the cracks start to form as this cycle, and along this line, we have a strip of FRP. So where this stays green along this line, that's debonded FRP. And we just push and push with higher and higher loads, and you can kind of see the FRP is very effective at holding this slab together. Even though it's cracking, we're still getting higher performance. And this right here is what kind of alludes to my big worry, right? This crack, if it was to propagate to where that anchor is, we lose this, and then you get your typical unreinforced failure. Didn't happen on this one, but I wish I had a video of it happening because it would be a lot more helpful. But yeah, essentially, I like the end anchors. I think it's great. You get the higher capacity. You definitely want your end anchors sized for rupture. But I would like to see multiple rows in case a crack hits it, and then distributed anchors, because again, if this was 100-foot long diaphragm, we're not actually touching anything out in the middle, and it's much better kind of engineering wise to distribute that and make sure everything's working together, pull as much ductility out of the concrete as possible. So this is the university study that we kind of went into after that, and this is an industry study that multiple manufacturers are involved with. Was that a cough or a question?
That was a cough.
Okay, gotcha. No problem. Oh my, so many things ruined. But here's the test setup. So there's actually a wall that's fixed, and then essentially a concrete collector beam here that's going to actuate back and forth. And again, industry standard type testing, we put end anchors on this specimen. It's roughly a 10-foot by 10-foot specimen. This is what it looks like when it's modeled, but basically, two specimens, you set the ram over here, you break this one, then you move the ram over, break it again, and that way we can replace and cycle through and get this testing done as quick as we can. So that testing all went through with just the one anchor, and it has pretty similar results to what we just saw. But we liked the study, and we wanted to do some more subsequent testing on the Simpson end out with basically the rest of the industry left out and just us in Virginia Tech, so we can study our detailing. And this is where things got fairly interesting for me, at least. So specimen CD7, we're moving more towards that recommended detailing that I like to, I guess, push on everybody. Instead of just one big end anchor, we have two rows of smaller anchors that are sized to rupture this fabric. And we're sticking with the same module, 10-foot by 10-foot. And then we're comparing it to a completely unanchored FRP system, because we already know what the one in anchor does, but we will really want to see how bad some of the old projects are and how big the need is to come in and fix those. So a little bit more like watching paint on these ones, and I'll fast forward some, but we're going to see out here, we're going to start to move back and forth, and I got to get rid of my laser pointer again. As it cycles, you're going to see on the right, the students at Virginia Tech come in and start to outline any debonded zones. And what you'll notice is there'll be a few lines at first. Right now is when it's starting. And then very quickly that whole inside debonds, and you'll actually see it on the left undulate and move around. So at that point, your anchors are really the only thing holding that system into performing. But we made this thing so strong with this solution that instead of having a typical diagonal shear failure, we get to the point where we have more of a sliding shear failure at the load point. And in the new ASC 41, you get a better M factor for that. So the one changing the failure mode's good because then we can help target what fails. But changing to a more favorable failure mode is great because it can reduce the overall load and the level of reinforcement needed. So this has great performance. We loved it. Still not quite the 100-foot scale I'd like to see it tested on, but there are limits to what you can test. And then when we compare it to the results of the unanchored test, let's see, did I have that video? I think I cut it out for brevity. On the left is our anchored specimen, And you can see we still get that diagonal shear failure, but when we go down below, the slab's pretty well held together other than where the load was coming in and we got that sliding shear failure. So that's on the left here. But on the right, the unanchored one, it got to its debonding strain and this whole magic carpet popped off all at once. And then the concrete did everything. And just in direct comparison, we still have the in-plane shear failure. But what concerns me is we also have large chunks of concrete falling on occupants. So we really like the detailing on the left and the ability to kind of target where things fail and kind of protect egress paths. But what does this lead us to is what can we do to increase resilience? Well, we know that when it comes under load, there's going to be a crack and debonding is going to propagate from that. We also know that if crack hits our end anchors only, we're going to lose that whole system entirely. So we, again, come in on a 10-foot by 10-foot module because that's what we've tested. And we start to approximate that 10-foot by 10-foot module with those smaller anchors again. So the load can still move past them, but if we get a crack and we get a crack here, we lose these anchors. There's a whole row of anchors to ensure capacity. And it just makes that post-peak performance a little bit more assurable. And it gets the actual performance promised by the equations up to where it should be. So this is what it looks like in practice. The images on the left or the right are just the two 0-90 layups that we would do to address loads in both directions with the industry standard end anchors. And then this image on the right is what we actually recommend adding on top of that for good detailing. And again, these are small pin type anchors, embedded type anchors, and we're just building them off of that tested roughly 10-foot by 10-foot module. So it starts being more engineering judgment for the actual spacing, but we try to build it economically based on the actual dimensions of the structure. So on this project, all of these smaller anchors does add a little bit of schedule time and cost. But on this project specifically, the material cost difference is only about 10%. Big FRP project, material cost is in the realm of 50 to 60% of the installation. If you go down to a smaller scale, materials are often 10% or less, and it's mostly labor. So it kind of matters what we're looking at on what we can design for you and try to find that nice balance of performance and economy. All right, we only have 4 minutes, so I don't think we're going to make through the shear wall testing. But you can kind of take a peek as I scroll through to my last slide of what we would have got to. And I'd be happy to come talk about this at any point. Oh, I love this slide. This is the test lab in Stockton. So to break a full-scale 12-inch concrete wall, you need, well, the full-scale 12-inch wall we did without FRP on it was over 800 kip capacity, and then you add FRP, which adds some capacity. So these are two 550 kip rams that we hooked up to this transfer beam, and they're there to break the wall. We built this rig for the structural steel connections that Simpson offers, and then to help with the FRP as well. But I love this picture because right here, that's a full ground person, and that just kind of gives you the idea of the scale of this sort of testing. And we'll keep moving. We did have good results. We actually did one 12-inch wall, two-sided with through anchors. And when we look at the hysteresis for that, we were able to get over 10 root F prime C. So that is potentially something that could pop up in the code down the line, but definitely don't want to promise it yet. And yeah, I appreciate everybody coming and paying attention. Future updates that I could come talk about. We have FRCM testing, our other composite system, much deeper dive into anchor testing. We're doing anchored beams for shear and flexure cyclic loading instead of just monotonic. We have a shear transfer truss made out of carbon that helps connect new concrete to old concrete. And then lots of study into various ways to fix kind of old mechanical bar splices or inefficient or insufficient laps that a lot of old buildings have. A lot of non-ductile concrete and masonry out there that we're hoping we can address. But that's basically it. I really appreciate it. And of course, if you have questions, I'm happy to answer them now or even later. You can just put my email in Teams and chat me pretty much anywhere I am.
Does anybody have any questions?
Yeah, I don't want to be the only one asking questions. Sure. Well, so you mentioned an M factor on the ductility of this reinforcement. What's the best M factor? Is the best M factor you can get with this system in line with a special reinforced concrete, or is it more like intermediate or ordinary? You know what I mean? Are you gonna, if you use it on a special reinforced concrete system, are you gonna lower the M factor?
So there's plenty of testing out there that shows that when you apply FRP to an existing ductile system, it only increases the ductility.
Okay.
We do not have testing to the point where we would be able to change like an R factor in new design by adding FRP. For ASC 41, we are working through testing to have M factors, but they're all, I mean, ASC 41 is going to be element application specific. So I think right now we have good M factors for shear friction type failures, and then in plane concrete shear reinforcement. You basically get a slight improvement on what the wall had before.
Okay, and the code will allow you to use these systems without reducing.
Yes, and it's going to be jurisdiction specific until it's actually codified. So if it's something you want to attempt on your project, you and I would talk about it, and then we go talk to whoever you're dealing with, the authority having jurisdiction to make sure they're comfortable, and we'll go through all the testing and everything like that. But yeah, it's not to the point where we could say, oh, by adding FRP, you're going to bump up to a better system, but we can improve the current one. And the real benefit that we see by proving deformation control on with FRP is right now all of the design guides say if you use FRP, you're in the force controlled realm already, which of course eliminates FRP from contention quite often because the load level is a little bit higher for force control.
Doesn't look like there's any other questions. Thank you.
No,
All right.
I had
Oh, wow.
cutting holes and shear walls question, but you pretty much answered it with the how you cut a hole in a diaphragm or, reinforce the outside. Basically, the gist of this is add a lot more anchors when you're using FRP.
Yeah. I mean, when it was first starting to get used in the US, people were all excited because it was something you could just glue on quickly and get a huge capacity. And that is true. If you use an 11-ounce fabric, you can get there. But as we start to test, we realize it's not quite the magic carpet everybody thought it was at one point, and we really do need to detail it, especially if you're in a seismic case. Wind's a little bit more predictable, gravity is a lot more predictable, so it's a little bit safer to go without the anchors, especially if you're up against economical constraints preventing the retrofit at all, right? It's much better to retrofit at a lower level than not retrofit. So yeah, we can have those types of discussions. But yeah, I typically, even if it was say like a positive beam reinforcement, I would still recommend putting the end anchors in. Because if that FRP debonds, which could happen due to large temperature fluctuations, moisture intrusion, any number of things, you lose the reinforcement if it's not anchored.
Typical to apply this from one side all the time or both sides all the time?
Well, the design guide wants to push it to two sides for certain thicknesses of walls and reinforcement configurations, but in practice, we see almost everybody pushing for one side. I mean, that could be for, a historical reason or aesthetic, but could just be practical. We think it's cheaper to do it on one side. So we focus our testing on one side specifically for walls. But when I go through that with you, you'll see, again, anchors are incredibly important. We did a 6-inch wall with 4-inch embeds, worked great as expected. Then we did a 12-inch wall with 4-inch embeds, and we got less than 5% participation out of the FRP because those embedded anchors weren't deep enough into the confined section of concrete to actually even engage, and the concrete fell apart before the FRP could perform. So detailing starts to be very, very important. none of it's really that complicated, especially if you look at an actual FRP count. There's no impressive math there. It's just a good understanding of what's happening and how things are going to behave, which is similar to all engineering. Yeah, I do have. Oh,
But
go for it.
A counter application where you would use this fabric to reinforce slab for gravity loads?
A lap splice for gravity or a slab for gravity?
Slab for gravity, just to
Slab.
increase the capacity or to limit the deflection.
Yes, limiting deflection is not well understood. When we look at our test results, FRP does tend to have a large effect on stiffness. It improves or makes things stiffer slightly, but you would have to add a lot to fix the deflection issue. But yes, you can use FRP on the strength side of slabs and for gravity cases, but it is passive reinforcement. So you depending on your case, if you're lightly loading and you're just changing a live load slightly, it's pretty easy to just put it on the bottom or apply it. But if you have a higher load gain, sometimes even jacking the slab, applying the FRP so it activates sooner can help. And then we are up against the ACI 562 existing capacity check as well. ACI 562 says any externally bonded reinforcement system and all FRP systems need to pass 3 serviceability load combinations. They're like 1.1 dead, 0.5 live, it's 1.1 dead, 0.75 live, 1.1 dead, 0.5 live, 0.2 snow, which will definitely affect you guys up there. And then there's a fire case where you're actually checking that serviceability load combination against your reduced capacity based on your fire. And if you can't pass those, then FRP is just out of the question entirely. It doesn't say we can fireproof or not fireproof. We can put fire protection on FRP for your slab and get you the 4-hour rating. But when you go and actually watch the UL tests, you pass and you get that 4-hour rating, but your FRP is entirely gone. And that's why that existing capacity check is so important to run. So if you were to come to me with a slab or any type of gravity reinforcement, that's, if it's not my first question, it's in the first 3. Have you ran that check and can we talk about it? Now, that's not to say that we can't help if you run that check and you don't pass. Simpson has partnered with a company called Structural Technologies that helps us kind of design alternate strengthening solutions. So we can do FRP, FRCM, externally bonded PET, member enlargements, and then combine all of those systems as well. We have a lot of tools. And really the message that I want everybody to have is if you have a complicated strengthening or repair project or any strengthening or repair project and you just want a soundboard, you can call me and I will give you any information that I can. And all that, that's no cost. We only make money if our material gets bought. Are there any other questions? I had one more thing I wanted to bring up and people will contact me directly about it if you're interested.
go for it.
So I am currently working a deal with ASCE directly for a reduced fee for their self-guided ASC 41 course. And the idea is I'm going to get a large pool of engineers that are interested, get that fee down as low as possible. And part of the negotiation with ASCE is that they're going to try to get the instructor to attend study groups that I'll run kind of along the length of the course. And the whole idea is, one, internally at Simpson, I'd like my team to get more up to speed on ASC 41 since we deal with it daily. And then in general, since we're doing it, we figure while we're learning, we can help everybody else in the industry learn alongside us. So if you have young engineers or you yourself are interested in learning more about ASC 41, please reach out to me. I should be kicking that off March 1st, or sorry, April 1st. I'm just collecting names for now.
Right. Thank you. We'll make sure they get that out to people that aren't here as well.
All right, well, if there's no other questions, please save my contact information and reach out if you have anything you'd like to talk about. And you'll probably get a call from me at your office at some point in the next 3 months, for me to come see you.
All right, thank you, Alex.
Thank you.
Yeah, thank you.
Thanks, everybody.
All right, hey, everybody, but SEAAK, I did get one update from Sterling I wanted to pass on to everybody because I asked him he can make it here today. Very low pass, this is, I'm reading straight from his text, very low pass rate on the first round of the SCE exam using computer-based testing, less than 20%. Sounds like it's partially due to conditions at the test centers. AELS is meeting with other state boards to talk about improvements.
Yeah, and I mean, that's
Nice.
one is, it's all electronic, Adobe PDF's screwing up all the time, right? Imagine taking a test.
Yeah,
Your PDF is crashing on you.
and the SE test was one where it's a lot of it was by paper, and they had the afternoon where,
Yeah,
it's all by hand.
I read the letter from Illinois. I don't agree with every point in there, but I think they probably should go back to a paper-based test. I
Or
think-
at least bring your own
Yeah.
code, because
Yeah,
you have
I
the
know.
recap, you have the.
You have one
your
screen.
notes,
One
you
screen,
have
yeah.
everything.
And then I think there was not all like the questions were actual questions. There was like sample questions or something like that. So it was like, why are you wasting your time with dealing with questions that don't account for the exam, right? Something like that I was reading.
But you have an hour longer test versus only 4 hours, like that was accounted.
Yeah, yeah.
Actual test,
It's also 21 and a half hours, right? I think
it's 5,
it's four.
it's
Four
5
sessions.
hours, 4 sessions, 5,
Yeah, so it's not a
4
15-hour exam. Now it's like a 21-hour exam or something like that. And they were saying they added more questions as just sort of like to help them with their little case studies or something like that. And it seemed like the first round, it's like they were just their key things and it's expensive. It's an expensive exam. And then you also have to take PTO off your, since it's 4 days now.
Yeah.
So.
yeah, looking at a 15% pass rate for the depth
Yeah.
for a couple of those exams is pretty off-putting.
Yeah.
Someone who,
Oh, no, yeah.
is supposed to take he's gonna take the seat.
Important to mark where the studs are at your house in case you go home and kick the wall.
Right.
You want to kick a stud? Just from what I heard, not from personal experience. All right. Any questions, everybody? Welcome back for the year and thanks for coming. Gonna get a couple other firms in here.
Yeah.
I think everybody's just busy right now.
So
I think it was.
coming back and trying to do, yeah.
There's.
Rich, I have a random concrete question for you. So,
Yeah.
place in Tampa, deep concrete piers, there's groundwater, additives. Yeah. C2M. I'm familiar with what would be good or what would, is there something I should be adding?
It's like, yeah. So it's like,
There's a big. You said the masonry, you have like five.
Yeah, no.
So you have a lot. Yeah, because you're going to bring in your own stuff.
Like, I actually don't fundamentally understand how it's both of them and say, oh, what are you gonna write down the answers that it's compromised?
I'm just interested. Search could be fun work with.
Yeah, I know, I mean, because I'm just now, I was major. Adobe and the search function and scrolling through a 1,000-page PDF document.
I still do.
Yeah, I know.
I still do physical red line.
Yeah.
You know,
You have to tap it out. So.
It's really fun project.
How are you doing?
Good. Yeah,
We have
well,
such,
oh, what did I do? Well, my car exploded.
Hey, see, right, I was in
it. That's what I've been
It's strangulation.
Yeah, that I can understand is that,
That
and
and
it
it's the
impact, when the impact.
calcium, sulfur, aluminum.
It's only at 45%.
Okay.
It's 3 times as expensive as Portland.
That,
We did a research
fuel
project,
line
CSA
structured,
people that make
dumped
everything.
fuel. And
And
you
we
have
took our bridge here, Mexicans, and
fire.
they optimized it for no shrinkage.
And the fuel tank.
No shrinkage.
This car, because it's a coupe. is
Initially, a
right
little
behind
expansion, but
Oh.
the
Basically.
tanks are still enough to hold that. And then,
Cut whole thing on fire.
That little extra expansion, that kind of chemical pre-stressing goes away as
So was
we're
that
end up with no stress in the concrete. So
or did you got
after, you know,
someone hit you?
so it's really cool stuff, and our permeability was
Hitting the curb at the
half
five, spinning,
what it was. without
spinning into the
affecting-
curb.
So just the 9.5% addition was permeability down. We ran it for 900 freeze-thaw cycles. The normal test is 300. At the end, freeze-thaw cycles, all four of these different concretes, we got about 4 different air concretes.
Yeah, that's one I'm most.
All 4 of them were still 100%. And most people say if you got 94%, the strength after 300 cycles, you're doing great. We ran 900 cycles with no deterioration. Type K, what's the type K? So there's some fun stuff you can do to make concrete extremely durable. I have actually 2 research projects going, one with Nima for Nina.
So this was
Yeah,
like.
he's one of the civil engineering professors. He loves working.
10
with
to
concrete.
15 seconds after. I'm-
So we got an enhanced durability project on with him. And then
I was able to get out
Our mitigation
by yourself.
plan
Yes, but that the driver's side.
Goes in, goes in, Sean Lee
Caved in.
developed the
So I
academic.
had to crawl.
They're the 2 chief chemists, Charles Fairbanks, Smith.
That's it.
They got a
Yeah,
machine.
that's the front.
So you gotta know what the core solution is. Of course, that will say a little bit
All
of,
kinds of skin crack.
gotta know the chemistry of that. Or some of the stuff.
So where.
They have a machine that compresses the concrete so hard it'll squeeze so.
Full.
Yeah,
They can collect it. But now and I just found out that they help sponsor a research project. They come up with a sensor now that you can embed in the concrete that will measure the pore water solution resistance. So you don't have to squeeze it anymore. And you can do it over time.
Full thickness. burn.
So we're gonna instrument some cylinders with those
Is
devices.
that their new engineering building?
Hmm?
Is that the new engineering building up there? They did the test? The new engineering
Yeah.
building,
Yeah.
Well,
I saw the floor, so my,
Strong floor.
yeah, my kids,
We don't need that. We're just doing these chemical tests. We all need to use the
unaffected down there.
The mass.
Which, you know, I would take,
Plasma. These chemical tests. There's a chemical test now for ASR. The old tests were
So, no, it's mostly.
early, were developed in the 70s. And they use these 1 by 1 mortar bars, so you can't use the roof. Grind up any course aggregate really small.
Now,
Yeah.
Make sand out of
I
it.
understand it because.
And after 24 hours,
Drive the door.
you put that little bar in,
You
a 1 normal sodium hydroxide.
So you
and then
So
this
going
No.
like here, yeah.
14 days, and then you test them.
And that's.
I mean, it's such a big test, like concrete isn't even set, it hasn't even made its connections. It's
Yeah,
very
it's
green.
pretty crazy.
It's, it's pretty interesting. So this test is way better. It's a chemical test, so I'll get on the aggregate.
Got a brain injury. It was, so
So
In a hospital
in the hospital, yeah, so they,
in Seattle, right?
in Seattle, yeah. So
Yeah,
they-
This is Nikolai.
they air
I
back.
gotta take this call, Richard. It's nice to meet you there.
yes, sir?
They don't have a unit here. No, my friend had heard a kid died, burned, and then they.
Okay.
Seattle, they don't have a unit here.
Yeah, terrible. Yeah. 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 For sure.
Yeah.
Oh, yeah.
Oh, you're catching me right out of walking out of a big meeting here. Let me close out of the